good afternoon for me. It's 6:38 p.m. As promised, I'm going to record myself going through some of the exercises in this book, which I recently arrived. And guys, this book is so good if you're anything like me and have struggled with intuitive explanations. I'm somebody who really prefers like a strong like mathematical explanation to algorithms. And I think that is a large reason why I have struggled with learning dynamic programming in the past. And recursion as well, because for me it just makes so much more sense when it's described in a mathematical way, with like formal language and everything, as opposed to like an intuitive way. That could be because I study engineering as well, but I don't think so because to be honest, like the math in engineering isn't like real math. It's just like calculus, which is, I wouldn't call that real math. I mean, I might get some hate for that, but um it's more of just an application of mathematical tools in my brain. Anyway, um this is just what works for me, and if it works for me, it probably works for other people too. So I thought that I would, record myself going through some of the exercises as I'm trying to teach myself dynamic programming. I don't really like know how to do it. Like I kind of know, and I've solved like a couple of dynamic programming problems before, and I've like learned it in class, but I don't feel like it really like resonated. Like I don't think I resonated with the way that it was taught, and yeah. So I guess this is me trying to formalize my understanding, if that makes sense. So yeah, I'm just gonna go through probably only one or maybe two of these exercises, and I don't feel like I don't feel maybe like super confident with them. Like I don't know if I'll be able to solve them. Um, but I think it's cool to record my process of going through them. It's something that I am trying to improve, like my ability to articulate while going through these types of problems, and yeah. So I will jump right into it. So this is these exercises are all in the context of like a rod cutting problem, and I'll just read that out. But essentially yeah, I'm just gonna read this. I think that's probably the easiest way. But okay. Selling Enterprises buys long steel rods and cuts them into shorter rods, which it then sells. Each cut is free. The management of Selling Enterprises wants to know the best way to cut up the rods. Selling Enterprises has a table giving for I equals 1 to the price of for I2 ongoing, the price of PI in dollars, that they always charge for a rod of length I inches. The length of each rod in inches is always an integer. Figure 14.1 gives a sample price table, and that is this table here. Okay. The rod cutting problem is the following. Given a rod of length n inches and a table of prices pi for I equals 1 to n, from 1 to n, determine the maximum revenue Rn obtainable by cutting up the rod and selling the pieces. If the price Pn for a rod of length n is large enough, an optimal solution may require no cutting at all. Consider the case where n equals 4. Okay. Figure 14.2, which is this one here. Okay, yeah, figure 14.2 shows all the ways to cut up a rod of 4 inches in length, including the way with no cuts at all. Okay, so this, yeah, it's all of the possible ways to cut a rod of length 4. Okay. Cutting a 4-inch rod into two 2-inch pieces produces a revenue P2 plus P2 equals 5 plus 5 equals 10, which is optimal. Selling Enterprises can cut up a rod of length 2 and n to the power of n minus 1 different ways. Since they have this is another thing. I was actually looking at this. Okay, can cut. Since they have an independent option of cutting or not cutting. Okay, so there's two choices. And there's n rods, but there's n minus 1 possible cuts that you can make. Okay, so they each have an independent option of cutting or not cutting at distance I inches from the left end. For I equals 1 from 1 to n minus 1. So I'm looking at my eraser button. We denote a decomposition into pieces using ordinary additive notation so that 7 equals 2 plus 2 plus 3 indicates a rod of length 7 is cut into 3 pieces 2 of length 2 and 1 of length 3. If an optimal solution cuts the rod into k pieces for some 1 is less than equal to k is less than equal to n, then an optimal decomposition is n equals I1 plus I2 plus I to the k. Okay. And this is about the combinations of of the choices. I love this book. I've been reading it like before bed for the past couple of days, and I feel like it's filling like all of the gaps that I've had in my knowledge. And it's I feel like it's really formalizing my understanding. But I only just started reading it, so I haven't really dived into the exercises yet. But yeah, so far I really like the way it's written. Okay. So if pieces are considered to be cut in monotonically increasing size, there are fewer ways to consider. For n equals 4, only 5 such ways are possible. What? Oh, okay, right. Like it's like if you have to have increasing size pieces, the number of ways is called the partition function. Which is approximately equal to, well, that's interesting. I don't really understand what's going on there, but I think I'm just gonna like move on to the exercises as I am on a bit of a time crunch today. So, okay, I'm not going to do this exercise because it's about time complexity and proving time complexity from like I think I could be wrong, but I think it might be like an application of Akrabazi theorem. That could be very wrong, but it's like a summation and like reducing a summation of like t and equals, let me find it actually in the book, equals 1 plus sum of n minus 1 I j equals 0 of t j, and then that equals to the power of n. And it's either like a summation identity. Actually, wait, I might just look at my summation identities. I think I have sum and overlay. Oh god. Okay. maybe not then. Let's just see. Let's just see if I can find it in my oh yeah. I actually do have the PDF. Okay. Of summation identities. Okay. Let me just add in my window capture. This is from my algorithms class that I took, like an advanced algorithms class. And I know that like I've taken an advanced algorithms class, but that actually doesn't mean anything, like I swear. It's not the same as doing LeetCode, and I found it really like difficult to learn in that environment. Okay. So I'm guessing it has something to do with this here, and let me just zoom in. Okay. There's a surprising amount of summation identities involved in like algorithmic analysis, which surprised me. Okay, I'm just reading them, and I think it's pretty much you just like pick whatever like identity like fits, but so sum of n minus 1 j equals 0 tj. Maybe it's just an, oh, it's a no. It's not a finite geometric series. I don't know actually if anything. Maybe it's just a I think what I have to do is like probably like do this. Let's see. I don't really remember how to do this. But you know, I may as well try for like 10 minutes or less. Okay. So it'd be like t of 0 is equal to what's t of j? Oh, it's yeah, okay, like equals 1 plus yeah, actually I'm pretty sure this is how you do this. So it's like 1 plus 0 equals 1. No, what? 1. Okay. That feels wrong, but anyway, t of 1 is going to be 1 plus 1 plus t of 0 is equal to 1 plus 1 equals 2. Okay, t of 2 is 1 plus t of 0, or sorry, t of 1 and minus 1. Plus, oh, that wouldn't be there. Plus t of 0 equals 1 plus 2 plus 1. Okay, is equal to 4. T of 3 is 1 plus t of 2 plus t of 1 plus t of 0. And now we're starting to see the pattern. It's just going to be 1 plus, like, everything else. But it's going to be, yeah, like 1 plus. Actually, I don't know if I'm seeing the pattern here. Because shouldn't that be, like, even? Hold on. Okay, 1 plus. What? Also, the actual question, it's like 14.4 is t n equals 2n eq. 14.3 is t of n equals 1 plus sum of n minus 1 to j equals 0 of t j. Okay, that's horrible handwriting, but hopefully it's somewhat legible. Maybe I don't know how to do this, but t of 2, okay, it would just be 4. Oh, actually, no, wait. I was, mistaken. I think I am starting to see the pattern, actually. So that would just be 6, 7, 8. Okay. Right, and, you can see that this is 2 to the 0, whoops. This is, sometimes it just takes one more recursive step. So this is, so 2 to the 0, 2 to the 1, equals 2 to the 2, equals 2 to the 3. See, engineering knowledge does help sometimes, especially when it's electrical. I guess actually I feel like I use binary way more in engineering though. Yeah, and then t 4 would be 1 plus 8 plus 4 plus 2 plus 1 equals 4, 8, 16 is equal to 2 to the 4. And that's how you can show that. Okay, well actually I did answer exercise 4.14.11. Awesome. Okay, great. I'm just gonna agree with that I got that correct because it's quite self-explanatory. And maybe I'll just move those like out. I don't know. It's like another page. I kind of want to save this up. Also, textbooks, underrated, like seriously underrated. I've never really used one before because I haven't really need to. I've only used one for electromagnetic waves and propagation because it was like such a good textbook. It like explained everything so well. Okay, what's next? I didn't get rid of my summation or my identities. Okay. 14.12. This is what I really wanted to do because I feel like sometimes when I'm in like a situation where I don't know if I need to use like dynamic programming or like a greedy algorithm, I'm not sure how to prove it, I guess. Okay, so the question is, show by means of a counterexample that the following greedy strategy does not always determine an optimal way to cut rods. Okay, define the density of a rod of length I to be pi divided by I. That is value per inch. The greedy strategy for a rod of length n cuts off a first piece of length I, where I is less than or equal to, 1 is less than or equal to I is less than or equal to n, having a maximum of, what? Let me just look in the book. Having a maximum density, there we go. Having maximum density. Okay. So, okay, let me reread this. The greedy strategy for a rod of length n cuts off a first piece of length I, where 1 is less than or equal to I, and I is less than or equal to n, having maximum density. Okay. Alright. It then continues applying the grading strategy to the remaining piece of n minus I. Okay, I think I understand. Just because I know like what a greedy strategy is, but let's just say, let's just draw it out. So let's just go for like a rod of length 4 using the same like pricing diagram, which is over here, and I'm just gonna copy and paste it over here. I've like lost the ability to crop stuff in OneNote, which is kind of annoying. But let me just do a cheeky screenshot. And I might actually want to keep this over here too. Oops. Okay. So, what do we do? Density. Okay. Value per inch. Alright, so okay, so it cuts off the piece that has the best like density, which is price per inch. Okay. You can tell this book is American. Okay. So like in this case, got a notification. Okay, so for this case, what would we do? We would pick this one because wait, no. So it cuts off does it always make a cut? Okay. Anyway, so it's going to make the choice that has the maximum density, and it picks it by seeing that, okay, if we have a rod of length 4, then that means we have access to a rod of length 3, a rod of length 2, and a rod of length 1. So out of those options, which one has the highest density? So a rod of length 1 is going to have 1 over 1 equals 1, and then length, okay, so 1, 2, L equals 1. L. Hold on. I'm gonna make a table. L D. Okay. So when length is 1, density is gonna be 1 over 1 is equal to 1. Okay. Then when length is equal to 2, we'll have density 2 over 5, which is approximately like, isn't it like 0.25? No. 25, 50. I don't know. 20 divided by 5 is 4, so it's 0.4. Okay, and then 3 will have 3 over 8, and what is it? 8 times 4 is 32, so it'll be like 3, like a 0.38-ish or something like that. Like, I don't really know. I don't have my calculator with me. 8-ish. I'll check. I'm trying to get better at mental math. Okay, hold on. But I should check. 375. That was pretty good. Okay, okay, 4 is going to be, 4, wait a minute. Am I doing this division correctly? It's been a long day. Okay, I say that every video, but that's because I always film these videos after long days. Okay, yeah, I'm not. It should be price over over length. My bad. Okay, whoopsies. Okay, 5 over 2. I actually okay, so that's gonna be what, 2.5? I think. 8 over 3. Yeah. That's gonna be what? 2.75? Something like that. Let me check. No, 2.666, repeating. 2.6. 4 over, okay, and then for a length 4, it's going to be 9 over 4. And that's going to be 2.25, maybe? Yes. I can do mental math, sometimes kind of. Okay, what's next? Now, because we have these options, okay, so it'll be like 1, 2, 3, 4, and or would it be like the density or the length that's the edge? I'm not sure. But I think it's the density actually. Okay, well anyway, basically we're going to pick this one. We're going to pick 3, cut off a length of 3. As our first option. So we'll go 3, and then that means that we have the choice. Oh, actually, okay, I know how this would be modeled. Okay. So it'd be 4, 3, 2, 1. No. What? I'm crashing out. Okay. Alright, I'm just gonna draw this path. So we would start with 4, and then we would cut off a length of 3, and then that would leave us with a length of 3 and a length of 1. Okay. And then this is like gotta be a cooked way of drawing this. But anyway, this total value is gonna be $9. And this one would be $8 plus $1 is equal to $9. Okay. And then what? Then we're gonna do the same for 3 and 1. Okay, this is not a good way of writing this. But I'm not representing like a choice here. I'm representing like an action. So it's like a state. So we, I don't know, guys. I don't know how to represent this. 4. We start with 4, okay? And then we cut 4, and we end up with this. We end up with 3 and 1. And at this stage, we have a total value of equals $9. So we haven't made any money by doing this. $9. Oh, I'm a mess today. Okay, now now from $3 we would cut off. We wouldn't cut anymore because that's our maximum value. From 1 we actually can't. Okay, so that is not gonna make us any money. But clearly this is a better value decision to make, despite this being the greedy solution. So this would give us a value of $10, and this one would give us only $9 by going greedy. So that is my counterexample. Okay, that was what's the word? That was a bit hectic, but we got there in the end. Okay. What's next? I don't know if I'm going to do that much more. I'm gonna read the problem and suss it out. How long has it been? 24 minutes? Okay. I'll read it. I'll see. No promises. Consider a modification of the rod cutting problem in which in addition to a price PI for each rod, each cut incurs a fixed cost of C. The revenue associated with a solution is now the sum of the prices of the pieces minus the costs of making the cuts. Okay. For each rod, each cut, and it's a fixed cost. Okay. Okay, so give a dynamic programming algorithm to solve this modified problem. So this is gonna be challenging, probably, seeing as I understand kind of how to do it, but we'll see. All right, let's just try. I'll try for a little bit. Okay. Consider modification of the rod cutting problem in which, in addition to a price PI, each cut incurs a fixed cost of C. Okay. Fixed cost of C. Okay. So we have, let's just go back to this, and then let's go ahead and just call C let's just give C a value, and we'll make each cut cost $1. Okay. What? So previously, the maximum value was like it was like a recurrence relationship that was written like this. I can find it in the book because I'm probably not gonna be able to derive it myself on the spot. So our solution is called revenue, and its variable is R equals revenue. Okay, and our objective of this problem is to optimize revenue. We want to maximize it. So Rn from the book, this is from the book, is equal to max Pi plus Rn minus I. Also, I is the length in inches, just so we are clear. Such that, what? Oh yeah, such that 1 is less than I is less than N. Okay. Or we could write that I in range 1 and inclusive. But anyway, we won't do that. Okay. And this formulation. Oops. The remainder. Wait. Okay, there's two ways to formulate this. So one of them is, I'll move this. So one of them is Rn equals max Pn R. Wait, what? Okay. R1 plus Rn minus 1. R2 plus Rn minus 2. Oh, okay, I understand, I think. N minus 1 plus R. No, minus R1. Okay. And here's an example of what they're oh, I didn't put it in there. Okay. Oh, yes. This is okay, so like for R1, so that's like of length 1. These are like the solutions. Okay. All right. Okay, now I'm reading the book again because there's actually 3 ways to formulate this problem. Okay, so I'm reading from the book now, and it's about this one, this the values for Rn, the values Rn for n is greater than or equal to 1 in terms of optimal revenues from shorter rods. Okay, ready? I'm going to say this sentence. More generally, we can express the value Rn for n is greater than or equal to 1 in terms of optimal revenues from shorter rods. So Rn equals max, and it's just this. Okay, and then below that it says, the first argument P of n corresponds to making no cuts at all and selling the rod of length n as it is. Okay, so that's the price of rod n. Okay. And the other n minus 1 arguments, that's these, to max. Wait. N minus 1 arguments to max. Oh, yeah, to n. Wait, what? I don't know. Correspond to the maximum revenue obtained by making an initial cut of the rod into 2 pieces of size I and of size n minus I, for each I in range 1 to n minus 1. And then optimally cutting up those pieces further, obtaining revenues I and R n minus I from those 2 pieces. Since you don't know ahead of time which value of I optimizes the revenue, you have to consider all possible values for I and pick the one that maximizes revenue. Okay, so it's like grabbing like the maximum. What? Okay, so like we don't know like which one is best, I guess. N minus 1 plus R1. Oh yeah, okay. I think I understand maybe. So it's like so revenue from 1 plus the revenue of n minus 1 is nothing. Okay. Oh, from the revenue of 9. So that's like what this would be. And maybe that's the maximum, maybe it's not. Or maybe it's the revenue from 2 plus the revenue of n minus 2, which would be 8. And maybe that's the maximum, maybe it's not. So it's like generally like the revenue of n minus 1. No, that's not general, sorry. The revenue from n minus 1, which is like wait, why do we have that again? I'm not sure why this is here twice, because that's odd, but I understand what's going on here. Anyway, you also have the option of picking no I at all if the greatest revenue from selling the rod uncut, which is this. Okay. Says you don't know, okay. To solve the original problem of size n, you solve smaller problems of the same type. Once you make the first cut, the 2 resulting pieces form independent instances of the rod cutting problem. Okay, yeah. The overall optimal solution incorporates optimal solutions of the 2 resulting subproblems, maximizing revenue from each of these 2 problems. We say that the rod cutting problem exhibits its optimal substructure. Okay. In a related, slightly simpler way to arrange a recursive structure for the rod cutting problem, let's view the decomposition as consisting of a first piece of length I, okay, cut off from the left-hand end, and then a right-hand remainder of length n minus I. Okay, so it's like we have a rod of size 4, and we cut off this, which is a size of length I, and then our remainder is this, which is 4 minus I equals 2. Okay, right. Okay. Only the remainder, not the first piece, may be further divided. Okay, why? Think of every decomposition of a length-in rod in this way. Oh, this is what the greedy problem was probably because we're only cutting the remainder, so like this gives us a remainder of 1. Like, so we go from having a remainder of 4 to having a remainder of 1 by cutting 3 for 2, 6. Right, okay, anyway. That's the greedy problem thing. Okay. I feel like actually I can maybe do this. I at least want to try a little bit more, just to have it go. Okay, alright. In this formulation, an optimal solution embodies a solution to only, wait. Okay, so in this one, it's like we have both rods. Like, so we have a rod, and then we create two distinct sub-problems like this that we then have to solve. And like each time you do it, you create two more sub-problems. Okay. So that is like probably the O of 2n thing, solution, time complexity, something to do with that. Because is that 2 of it or log n? I don't know. Anyway, but this one, it's like, okay, we make a choice, and then now we are left with just this. So like we cut that. Wait, it's not a great way to explain this. So like we decide to cut that, and then we're left with this. And then we decide to cut this, and we're left with this. If that makes sense. It kind of does to me. Okay, only the remainder, not the first piece, may be further divided. Think of every decomposition of a linked-in rod this way, as the first piece followed by some decomposition of the remainder. Okay. Then we can express the solution with no cuts at all by saying that the first piece has size I is equal to n and revenue P of n, or Pn, and that the remainder has size 0 with a corresponding revenue R0 is equal to 0. We thus obtain the following simpler version of equation 14.1. And this was EQ 14.1. Okay. And then this is the simpler version. Okay. So, R of n is equal to the maximum of the price of I, where I is the first piece that's been cut off, and then R n minus I is the remainder, for all I is greater than 1 less than n. Okay. I think I understand now. It's pretty much, like P, and let's say, let n equal 3. So we'd have P1 plus R2. So it'd be like max. P2 plus R1. P0 plus R3. Right? And R1, so let's say R2, it would be P and then yeah, forgot to do P3. This would be at the front, but anyway, P3 R0. This wouldn't be here, I don't think. Oh, it could be. Nope, it can't be. Because I has to be greater than 1. Okay. So, 2 would just be, P2 plus R0, max. P1 plus R1. and then it would be the same for R1. It would just be P1 plus R1. Whoops, R0. It'd be just that. Okay. Alright, so now how can we optimize this for the number of cuts? It's going to be quite similar. Or for when cuts cost money. So instead of taking, also I'm going to delete this because we don't need that. And I'm going to move this up. So I'm guessing like instead of like taking the maximum of pi plus r in minus I, we're going to be changing that like recursive structure. So it'd have to be like max. Let's just let n equal 2. So like we'd have like a rod of length 2. So that's like quite a simple case. Or like a rod of, yeah, that's like 1 cut. So R2 equals max and I'm gonna sub these actual values in. So P2 plus R0 plus. Alright, and then that would be P2 plus R0 is 5 plus 0, and then 0 plus, no, P1 plus R1 is 1 plus 1. So this is without cuts, and with cuts, we would have to consider R2 So with cuts for R of 2, it would be max. So like we now have a choice. It'd be like P2 minus I think that it like maintains the like substructure. What's it called? Optimal substructure, where like each optimal solutions to a problem incorporate optimal solutions to related subproblems, which you may solve independently. Let me go to like the subproblem graph page, because like if we have I'm gonna draw a subproblem graph. So like if we have 4, 3, 2, 1. This might be too big, but 0. I might take some of these out. So like problem, yeah, let's simplify. Problem 1, it's like you need to know. Okay, if I think of it in the like remainder way again, it's like we only want like, okay, if we cut, like if we make a cut and the cuts cost the same always, then it shouldn't really matter because like we are only gonna make a cut if pi minus c is greater than, so okay, make cut if pi minus c is greater than the revenue from, no, if the revenue of no, okay, pi plus, no, pi minus c, what? Cut on rod length n if equals len of cut. Okay, if we're at like a rod of size 2, for example, and the price of rod of size 2, let's say it is we could get $4 for like a rod of length 2. No, $3. But then a rod of length 1 would give us $1. And if C is equal to, or let's actually make this like $2, $2.50. Okay, so if we cut this into 2 rods, then we're gonna have 2 rods of $1 each. Yes. Wait. This is what I meant to do. Alright, yeah. So we will have 2 rods of size or price 125, so that would be $2.50 instead of $2. But we will have made a $1 cut. So our actual profit is going to be 1.25 times 2 minus $1 is going to be $2.50 minus 1 is equal to $1.50. So that's actually less than our PI, which is price of rod of length 2. So we wouldn't make that choice. Okay, so so we want to take the maximum of so for n is equal to 2, which is like a very simple case, we would take max p of 2, which is the price of n equals 2, or the price of plus r of 0, because no cuts, or p1 plus r1 minus c. Okay. I feel I don't know how to do this. Max p3 plus, so this is for n equals 3. p3 plus r0, p2 plus r1 minus c, p1 plus r2 minus c. Okay, this makes sense because each time we're cutting, we're like going to have to subtract. And so like if we were writing this in code, we would do what would we do? Like, okay, let's just say we have all of these like available to us. It would be the maximum of, and also we already know. No, wait. We already know like the outcome of this question mark is gonna like rely on this. Hold up. Because alright, so we're gonna be keeping like a table, obviously, of like max rev. So like 0, 1, 2, 3. So for 0 it's $0. For 1 it's 1.25. For 2 it's it's $2. And for 3, what is it? Well, okay, we have to set a value to 3. Let's say 3 is like also like okay, 3.25 minus 1 is 2.25. So let's say 3 is $2. Like cost $2. Oops, I meant to do $2. Then clearly we want to cut it because we'll end up with $2.50. I'm cutting it, wait, $3.50, which minus the price of cutting will give us $2.25. Okay. And that's our revenue, but like, what's the actual like profit? The actual profit, what did I say? Yeah, it's 2.25. So that will already consider like the cost of cutting. Okay, so, whoops, just turn my laptop off. Or not turn it off, I just locked it, that's what I meant to say. Alright. I think this will be the last problem that I solve from these today, just because it's kind of taking a while. I'm sure this shouldn't take this long, but that's okay. It's a learning process, isn't it? Okay. So like, what do we do for 3? For 3, we look at the price of 2 and the price of 1, and we add them, and we subtract however many, like, cuts that would need. No, for 3, we look at 2, the price of 2. Okay, and then we also will have a remainder of 1, so we look and we add the price of 1. And then from that, we are subtracting the cost of cutting, and we're comparing that to the price of 3 without any cuts. So it would be like max P. Oh, but we also would want to consider the case where we like have 3 separate cuts. Guys, I don't know how to do this. Okay, so like we have 3. Okay, so from that we could do this. We could do we could either keep 3 or we could do 1, 2, or we could do 1, and from 1 to we could go 1, 1, 1. Okay, that's our like options. And I don't know why it's like a graph, but it's it's because we're like cutting this. It's like 0, 3, I guess is a better way to write it. Um okay, what? I'm gonna give myself a time limit. I have 10 minutes, okay? 10 minutes. Can I do it in 10 minutes? Uh, God, I have to give an algorithm too, bro. Um, okay. Alright. What's our subproblem graph? That's a good question. So like, with 0, that relies on nothing. With 1, well, we're going to have 1 with a remainder of 0, so that does rely on 0. Because it's going to be just the price of 1 plus the price of 0, which is $0, obviously. And when we're looking at 1, it'll be the price. No, we can't cut it at all. Okay, and then for 2. 2, we're either going to make a cut or we are not going to make a cut. So that's our graph. And then 3. We are either going to make a cut into, like, and have a remainder of 2, or a cut of size 2, or we're going to make a cut of size 1, or we're going to make a cut of size 0. And if we make a cut of size, 2, Then we have two options. We can either make a cut of size 1 or of size 0. And then etc. etc. So solving 0 will give us the method to solve 1, and solving 1 will give us the method to solve 2. Because with 1, so with 2 it's like we're either gonna like do like this and then like take the maximum of that again. So it's like, okay, actually let's go with 3. Okay, let's say, so we have already found that like cutting is the solution into size 2 and 1. So like we can see that like 2.25, 1.25, 0. We're gonna do the one that is gonna give us 2.25, I guess. That seems like the greedy solution though. I guess it's not, because we like already know that like the price of 2 is like already considering like the cost of cutting. Uh, Guys, I'm stuck. So it's like max. How would we like write this out? For case 2, what would we do? Well, we're either gonna cut or not. So like we're either gonna take 2 and the revenue from 0 with no cuts, or we're gonna take 2 and the revenue from 1 because we're making 1 cut. And we don't know if 1 made any cuts or not, but that doesn't matter because all we care about is the fact that we are now making a cut. And from 3, we are either going to take 3 with no cuts, or we're gonna make 1 cut and we're gonna take the revenue from 2, and then we're gonna deal with like our remainder, or oh, so if our remainder was of size 2, okay, this, okay, this would be like what we're like looking at, and then this is like our like leftover. So like we're like looking at like 2, so the optimal like money that we can get from 2 is $2. I'm a little confused because like, what if, for example, with 4, oops, this is like not all of the ways that you could cut. Like, why aren't we considering, for example, like R3 plus R1 minus C? I think we are. I think I'm just misunderstanding the notation. Okay, I'm gonna read the book again. I actually need to stop. Like, I actually need to stop. But I'm gonna read the book again. Okay. Okay. I read it wrong. I read it wrong. Okay. This is what you get for skimming stuff and reading stuff when you are tired. Um, PI and RI are not for price and revenue. Both of these variables are representing revenue, I believe. It's like PN. Uh, so let me find where it says. Wait, no, yeah. So like this is like the remainder. Wait, no, okay. Actually, I didn't read it wrong. I didn't read it wrong. So remainder rather than two. I don't understand how like that other equation can be reduced into this. Uh, okay, so it's like because we're always gonna have either no cuts or like at minimum a cut of size 1. Um, okay, and this is the equation 14.1 by the way, and 14.2 is this one here. Okay, we're always gonna have at least one cut or no cuts. Okay, true. Um, and this is like the sum of the remainder of the revenue from 1 minus 1. Okay, revenue from R2, R9 minus 2. I'm not sure like how that gets like two sub problems. Like what? Okay, let me read it. The first argument, this is about this. The first argument, P of n, corresponds to making no cuts at all and selling the rod of length n as it is. Okay, yep. The other n minus 1 arguments to max. What? Correspond. Oh, the other n minus 1 arguments to max, like to take the maximum of. Correspond to the maximum revenue obtained by making an initial cut of the rod into two pieces of size I and of size n minus I, for each I in range 1 to n minus 1. Then optimally cutting up those pieces further, obtaining revenues for Ri and n minus I from those two pieces. Since you don't know ahead of time which value of I optimizes revenues, you have to consider all possible values for I and pick the one that maximizes revenue. Okay. I'm a little like I kind of wish they expanded to like 3 or something like that. I guess it's not necessary, but anyway, like how do we get here? N minus 1, 1, like that's literally the same thing. Um, I think that it would be this equals max pi or p so p n um Does that make sense? Because now we have like two, whoops. Like it's gotta be like this. So like this would be like either like the price, like just the raw price with no cuts, or the price of a subsection plus the revenue of like the remainder minus, so like the revenue from a subsection plus the revenue from the remainder minus the cost to cut that. And this can be further divided, and that's considered in like the sub problem, because like r in like n equals 2 might equal r n equals 1 plus p n equals 1 minus c. Or it could equal r equals well, r n equals n. No, sorry. N equals 1 is what I was trying to do. Yes, n equals 2, my bad. Could be equal to r n equals 0 plus the price of n equals 2, but not minus c. It's whichever is the maximum, and this will get both, as long as we have n minus 1 here and p of n here. And I believe that this would work. And how can I prove that inductively? This is something that I don't really know how to do. Characterize the structure of an optimal solution. Cursively define the value of an optimal solution. I think I've done that. Compute the value of an optimal solution, typically in a bottom-up fashion. Construct an optimal solution from computed information. Okay, let's just try this. I think there's solutions in the back, maybe. No. There are. I know there's solutions. I read about it in the first chapter. Let's see. Are there solutions? Where are the solutions? Where are the solutions? Okay. I think that like maybe the exercises like maybe don't have solutions. So yeah. I might check. I'll check online. Okay. Well, somebody has like all of the solutions here. Hopefully has yes. Great. Wait, what chapter is this? Uh-oh. This is from 2014 or 2016, and I think that this is maybe changed since then. Yeah, this is not the same. Damn. When is this from? Okay, maybe maybe I can like hack this system by like going to 15. Yes. Yes. Okay. Oh! Wait. I may have cooked. I may have cooked. Alright. I found some solutions. The captcha. Let me check. Oops. Is it actually making it smaller, or is it just... Okay, no, that wasn't making it smaller. Okay, here are the solutions. It used to be chapter 15, but now it is not. So I'm just gonna check. Is it the same? It's not written the same. That is for sure. I can't see it because I'm on OBS, but okay. Rn equals max. Wait. Oh my god. Okay. If I cooked, that's so awesome. R of 1. Okay, I think that I've written pretty much the same thing here, but like, like maybe not, but like I'm pretty sure like this is what I like meant slash wrote, but just in kind of like a weird way with this like nested max statement. But yeah, so it's just the price of n, and then it's like plus 1. This is the other way to write it, this one. But I tried to write it in this way, which like I'm almost like positive this is the same thing, like just maybe a little bit less conventional. Anyway, I haven't done this part, but I'm content. I didn't do that part because I just wanted to solve the formulate the recurrence relationship. Okay, I'm gonna give myself like half mark on that. Okay. I'm not gonna do the rest of these. It is too late and I need to go to the gym. So thank you for watching. I had a fun time solving these problems. Believe it or not, I do actually enjoy this. And yeah, I think I'm gonna probably continue to record the process of going through the exercises in this book because it's pretty fun to go through them, and I like talking through the solutions. And I'm more inclined to do it when I record it as well. So yeah, thank you for watching, and I'll definitely be making more of these. And if you made it to the way to the end, then I'll probably see you next time. Thanks.